Hello? Okay, then. Let's get started. I'll talk about the subseasonal or intraseasonal variability of the South American monsoon. Just to show you some background, well, this you have already seen yesterday, the intensity of the monsoon, the domain of the South American monsoon. And here you have a picture of the topography in South America. I'm showing this because usually when one talks about topography in South America and its importance, its influence, people always think about the Andes here, which of course are very important in shaping the circulation over the continent. But we have also other topographic features here in central East Brazil, which are very important in shaping the circulation, the monsoon circulation over this region here. So keep in mind these topographic features here in southeast Brazil. Here we have the sea mountains, the central plateau. So this is a rough topography, actually, not as the Andes, but it has influence on the circulation. Well, just to show you the main features, to remind you of these main features of the monsoon system. In austral summer, we have a thermal low pressure system intensifying here over the Chaco region, thermal low, continental low, and the tropical northeasterly trade winds strengthen. So here, the tropical trade winds. Cross-equatorial flow penetrates South America, becomes northwesterly at the Andes foothills. So here, cross-equatorial enters South America, becomes northwesterly here at the Andes foothills, and turns clockwise around the Chaco Low. So the low-level wind and moisture conversions associated with interaction between this continental low here and the South Atlantic high, and these northwesterly winds here result in an enhanced precipitation in the Amazon and central and southeast Brazil, this core monsoon region, as you can see here. This here is observed rainfall for summer. And I want to emphasize here that here in the core monsoon region and here over the South Atlantic convergence zone, you have around, let's say, 10 to 12 millimeters per day on average. And what we also emphasized yesterday as a characteristic of the monsoon is the reversal here close to this core monsoon region from zonal easterlies to zonal westerlies. And this is shown here in the figure also shown yesterday by Manuel Gunn. So this reversal of zonal easterlies to zonal westerlies here is responsible for bringing this moisture flux into this monsoon region. So it's very tightly connected with the monsoon precipitation, this reversal of the zonal low-level wind. So if we have any factors that affect these westerly winds here, which bring moisture into this region, which is responsible for this monsoon precipitation in this region. So an aspect that weakens or strengthens this zonal westerly component, is prone to influence the monsoon precipitation. And well, there are different aspects that could modify, strengthening, or weakening this zonal component. We could, for instance, have zonal winds coming via Kelvin waves within this region via equatorial teleconnections. We could have a deepening of this low for any reason. We could have extratropical wave trains producing anomalous cyclonic circulation here in this region, thus strengthening this zonal component. So there are different ways of modifying this zonal component. Okay. To show you how this aspect of circulation is important, we define it for other purposes. I will talk about this on Thursday, about the predictability and prediction of monsoon rainfall here. So we define it for this purpose, a monsoon precipitation index. Here, in this region, was chosen as a compromise between the region where the monsoon precipitation is strongest and also where it has the strongest intraseasonal variability. So when we look from the point of view of intensity of the precipitation, it should be a little bit more to the west. But when we look from the point of view of variability, this index should be a little bit to the east. Therefore, we chose this region as a compromise between these two conditions, variability and intensity of the monsoon precipitation. Okay, so when we look at the rainfall series within this region, daily rainfall series, daily. And if we separate the days with active monsoon or break monsoon, define it as standardized anomaly. So it's an index above +1, below -1 for active and break monsoon periods, days. So if we composite OLR anomalies for active monsoon days, this is what we get. When we composite for break monsoon days, this is what we get. And this is the first intraseasonal mode of variability in the band of 10 to 100 days. If you calculate from 20 to 100 days, you will get the same thing. So you can see that the composites for active and break days reproduce pretty well the first intraseasonal mode of variability. So this index in this region really reproduces very well the variability of the monsoon. So let's see what kind of circulation anomaly, zonal wind, low level, is associated with variability here. So if we correlate this monsoon precipitation index here in this region with zonal wind at 850 hectopascals, this is what we get. And so you can see that really here, westerlies in this region are prone to intensify rainfall here. And of course, easterlies will weaken, will lead to break phases. So then, let's show you what's the contribution of intraseasonal variability? Why is it important? We know about synoptic variability, which is very important when you look at the contribution of synoptic variability to the total variance of summer rainfall, daily summer rainfall. You get these proportions. Of course, you can see that over most here of the continent, especially on the western part, you have very high contribution here from synoptic variability. But you have also lower contribution here on the eastern part, here, especially over Central East South America, here. And also here over the northeastern part. So this is the contribution of synoptic variability. When you calculate the contribution of intraseasonal variability, you can see that where the synoptic variability is weaker, has a lower contribution, you have stronger contribution of intraseasonal variability. And this intraseasonal variability can contribute up to 50% here of the variability in this region, here in Central East Brazil, which is a very important region because it is part of this monsoon region, is part here of the South Atlantic convergence zone, and also here the southern part of Northeast Brazil. So, well, and of course, it also contributes a lot here in southern Brazil as well, and here in the core monsoon region. You can see that there is a very significant contribution there. Then, well, let's see what is this intraseasonal variability of the South American monsoon. Much of these results were produced by a student of mine, Simone Ferraz. So, why study this intraseasonal oscillation? I can tell you that the extreme precipitation events actually have contributions of intraseasonal variability. It's not just synoptic variability. It's a combination of synoptic but modulated by intraseasonal. I will show examples at the end of the presentation, this interaction between intraseasonal with synoptic. Okay, well, it contributes to urban floods, to agricultural droughts, even energy shortage. So this intraseasonal variability is very important since, well, most of the continent, most of Brazil, is under a monsoon regime, and most, at least 55% of annual precipitation falls in the summer. So if we have, for instance, intraseasonal variability producing long periods of dryness within the monsoon season, it could have dramatic consequences, or even for above normal rainfall during the monsoon region. Well, we want to see intraseasonal variability during the summer precipitation from the point of view of its contribution to the variance, the principal modes, the composites for extreme phases of some modes of the most important ones, and some dynamic considerations. Well, here are the data. These are all observed data we are using to calculate this variability. It's a rather long period for intraseasonal variability, at least. Well, the data were filtered according to different bands within the intraseasonal time scales. So synoptic, 10 to 20, 20 to 30, and then the MGO, the longer period band. So to see the relative contribution of each of these bands. Actually, we have different mechanisms for these different frequency bands within intraseasonal variability. Well, this is the figure I showed you before, showing that where the synoptic variability has lower contribution, we have stronger contribution here from intraseasonal, and here just to complete the interannual and higher periods contribution to total variance. Oops. And okay, so here you have an idea about the contribution of the different frequency bands within the intraseasonal variability. Okay, in the synoptic, as we saw before, the major contribution is here on the western part and here in the southern part. Here in this band, 10-20, more here, also in the southern part and also western part. Then 20-30, there is a region here with very significant contribution. And 30-70, well, the South Atlantic convergence zone, and here Central East Brazil, and mainly South Atlantic convergence zone and Northeast. You will see the reason for this later. So we will show you the results of EOF analysis. We will rotate these EOFs to separate better different mechanisms and show some extended EOF analysis to see characteristics of propagation. So here you have the first EOF in this 10 to 100, the whole intraseasonal interval, and then these sub-intervals here, 10 to 20, 20 to 13, 30 to 7. In all these intervals, this is the first mode, this dipole mode between Central East South America and Southeast South America. It's the most important mode in all these bands of variability. This is the second one. Do you remember that this 20-30 day band had a great contribution here over São Paulo? So you can see that it has the largest explained variance here for this mode, which has the highest factor loadings in this region. So these are the first and second. I will show just these ones for now, for the non-rotated modes. And well, here you can, let's see if it works. You can have an idea of how these modes propagate. Oops. Let's see how I can do it. There. As you can see, it propagates northeastward over the continent, here in the eastern part of the continent. So it's something probably related with extratropical waves. Then it propagates northeastward over the continent. And now let's see this here. And you will see that same things happen. Northeastward propagation in this slower band of variability. But now, for MGO time scale, 3070. Look what happens. It's stationary oscillation. Huh? And you can see some separation, which will, because this is not rotated. When we rotate this mode, you will see what happens. Oops, no, that wasn't what I wanted. So here we were. Now we rotate these modes. In the 10-200 day, so the entire intraseasonal band, these are the first four EOFs of this band. These are not rotated. Remember, I showed you these first two here. And when we rotate the modes, we get this one here, separated in two others. So you can see that it's not the same mechanisms that produce variability in the southern part and in the northern part of this region here. So in the southern part, over the South Atlantic convergence zone, we have one mode. And in the northern part, another mode. So this one is separated by a rotation. And then this here is more or less the same. And we are displaying here the third first, and the fifth, because the fourth doesn't appear, the fourth in the 100-day band, it doesn't appear as one of the first 5 in all these sub-bands. So this here seems to be more important, actually. Okay, here you have an idea of the contribution of each of these modes to the variance. You can see that these two here, this here is the first one in the entire intraseasonal band, and is the first one in 10 to 20 and 20 to 30, this. But this is the first one in the 30 to 70. So when you go to the MGO time scale, this here turns more important. Well, and here you have the contribution of the other ones. This here, for instance, okay, this one is in the 2030, has a something. Oh no. Okay, so here I am showing you the first two. Here the first two in the 30 to 70 band. Yeah. This one was the first, this one was the second in this band. And here you have composites for the wet phase, so when it rains above normal here, and the dry phase for this first mode, here. Oh, it's wrong here. This should be 1 here. Okay, consider 1, here 2. And you can see that it is related to extratropical circulation. You don't see here equatorial connection. This, which appears in a dry phase, is very, very small here. And here you don't see anything significant. And here you can see this extratropical connection for this mode. Whereas here, in this one, you can see that this equatorial connection is really very important. Here. So the westerlies associated with enhanced precipitation, the easterly with less precipitation. Now, let's see what happens with rainfall, daily series, in these regions which have the strongest loadings in this mode we called northeast-south. So in the southern part of northeast Brazil, this is the mode of the South Atlantic convergence zone, and this is the mode of the south. So the average daily precipitation over these regions here are an index we will analyze and will compare with the factor scores of these rotated modes. And well, as expected, we see that these modes represent very well these extreme events in these regions when we have 1.4 standard deviation plus or minus of rainfall, standardized anomalies. So as expected, these modes represent very well the anomalies of rainfall over this area. Now, something interesting here is that when you look at the non-rotated mode in which these two modes were merged into one, the first one, we had a very strong dipole-like mode. Just to, I think here it is. Here, this was the first non-rotated. With rotation, it's separated into these two. And you saw here that there is a very strong dipole-like structure. But when you rotate it, you don't see a real dipole, because the factor loadings here to the south, although of opposite sign, are not strong. So let's see if we really have a dipole here between these regions and also these ones here. That's something we look into with these indices. So here, the rotated modes do not show a real dipole-like variation between the sacs and the subtropical plains, as I showed you, which shows that rainfall anomalies in these two regions, in the sacs, in the subtropical plains, are not always connected. Not always more rainfall in one of these regions means that you have the opposite anomalies in the other one. So to verify the dipolar character, the number of extreme values of the index of sacs, so above 1.4 standard deviation, below minus 1.4 standard deviation, that corresponds to extreme values of opposite or same sign of the south index was counted. So what did we get? 22% of the extreme events in the sacs correspond to extreme events of opposite sign in southern Brazil. So just 22% of the times we had a real dipole. And, well, only 2% of the extreme events in the sacs correspond of extreme events of the same sign in southern Brazil. So, of course, the tendency is to a dipole, but not necessarily we have a dipole always. And here we have composites no composites, lagged correlations. Oops. Yeah. Lagged correlations keyed to this index of above normal rainfall here in the southern part of northeast Brazil, here in this region. The this first mode, rotated mode of the entire intraseasonal band. So 6 days before, what do you see here? You see, well, this is OLR, and you see here positive anomalies, so subsidence here, negative anomalies here, extending into the subtropics. And it's possible to see 4 days before, well, here you already have something forming here. But 4 days before, you see this equatorial connection here, which gets stronger here, -2. And you see this extratropical wave train forming here. So you have here then a cyclonic circulation. On day 0, it's very strong, elongated here. You have this elongated circulation stream function here. So what seems to be the main mechanisms is the equatorial propagation, in this case here, but there is also an extratropical component. Now, when we go to this, well, okay, there is another. When we go to this index of the South Atlantic convergence zone, so now the convection is more to the south over this Atlantic convergence zone, you don't see equatorial connection, but you see a very strong extratropical connection here. And it also, here it starts forming, it's formed already in day -4, but then it gets fully established here with this cyclonic circulation in day -2. And then in day 0, when you have the maximum convection anomaly here, this wave train dissipated, but you start seeing something coming from here. And from here, we have connections to Southern Africa. And what about this mode, this southern mode? This intraseasonal variability in southern Brazil, in the sub-extratropics here. Well, you don't see any extensive or very significant equatorial or tropical convection here connected with this. So it seems to be really connected with extratropical waves that for some internal variability, atmospheric circulation variability, reinforce this kind of wave train. So the origin of this intraseasonal variability is not yet well understood. Parts of it, yes. Mainly here, these 30 to 70 days. But these other bands here are, the origin is not well understood. So the higher frequency bands, these here, seem to be associated with internal fluctuations of the atmospheric circulation, whereas the lower frequency band is associated with MGO. Is there remote influence? Well, yes, there is. There is contribution, at least. The first two modes, I show it, the correlation with the stream function anomalies. They seem to be related to wave trains propagating southeastward from west or central Pacific, rounding the southern tip of South America and turning toward the northeast as part of larger scale systems whose associated convection in Central East Pacific may originate or modify those wave trains. The first mode, that one associated with enhanced convection in the southern part of Northeast Brazil, not over Sax. Southern part of Northeast Brazil is also related with equatorial Kelvin and Rossby wave propagation. So due to this intraseasonal variability, regional circulation, and an example is the South America low-level jet, may be modulated by intraseasonal fluctuation of zonal flow above the Andes and consequent fluctuations of the orographically bound cyclone east of the Andes. So we can have this intraseasonal variability in the South America low-level jet. Is there intraseasonal variability associated with local forcing in South America? Yes, there is. I will show an example if I have time. So simulation with a regional climate model showed that there are links between soil moisture, surface temperature, and regional circulation that lead to observed intraseasonal oscillation. And this is very much connected also to topography in Southeast Brazil. This topography I showed you there in Central East South America. This topography is important in shaping the associated circulation and precipitation patterns in this effect. Okay, so now that we look at the different bands and how they behave, how they contribute, let's focus on MGO in the 30 to 70 day band. We separated the MGO cycle into 8 phases. I guess most of you know this procedure. It was proposed by Wheeler and Hendon in 2004. They used the multivariate EOF analysis of OLR and zonal wind at lower and higher levels in the equatorial region, equatorial belt. And after removing annual cycle, interannual variability, and the data were normalized by the standard deviation. So the first 2 combined EOFs describe this propagating MGO structure. And there are 2 indices that are calculated by projecting these variables onto the first 2 combined EOFs. And phases are defined according to the combination of these 2 indices. And so we did composites for each of these phases. Here you have an idea of these 2 EOFs from Wheeler and Hendon method. And here you see how the phases from 1 to 8, they are distributed according to the contribution of this index, RMM1, and this one, RMM2. And here you have an example of one MGO episode. These dots are the combination of these phases for each day. So here you can see how the MGO evolved through these 8 phases in this event. When these dots are within this circle of amplitude less than 1, one considers that there is no MGO. It's a neutral phase, let's say. So here you have divergence anomalies from phase 1 through phase A. And you can see very easily, this is a very, well, it's not so well known for divergence at upper level, but it's well known, this kind of figure, for other variables. I show it here, the upper level divergence, because this is important to explain dynamically some teleconnections we will talk about. So you can see here, for instance, that in phase 7, So these upper level diversions are associated with anomalous convection, and this is upper level conversions associated with anomalous subsidence. And here in phase 7, you see that these upper level diversions, so the anomalous convections, enters here, crosses the date line, and shifts into the subtropics of East Pacific, east of the date line. And the upper level divergence is spread here and is significant in the subtropics of Central East Pacific. So keep this in mind. And this is connected some days after with enhanced convection, so upper level divergence in phases 8 and phase 1, which are the phases with most enhanced convection or precipitation over the most extensive regions in South America. Here you have a picture of the propagation of the centers of, here is velocity potential at lower levels. So you have centers of convergence, anomalous divergence. Now, it's more or less a number 1 pattern, although not strictly talking. So here you can see you have anomalous convergence center in phase 8 and 1 here over South America. And at the same time, anomalous low-level divergence over the maritime continent. And here you can see the propagation of OLR and zonal wind in this band. Usually people draw these Hofmeller diagrams on an equatorial band centered on the equator. But this doesn't give a very good picture of the displacement, the propagation of, and I can show it very easily. These here are OLR. So if you get the average from, for instance, 10 degrees north to 10 degrees south, here you have already nothing here in this region. And here, for instance, over Africa, and there are many instances where you lose information because you are taking the average center on the equator. It's important, as we see very clearly here, that the strongest anomalies are south of the equator during the austral summer. It's very important that we take this average south of the equator. Then we really represent these most important anomalies here, the propagation of these most important anomalies. So here you have the propagation of the convection, well, represented by OLR. So it propagates there in the Indian Ocean and the Western Pacific, eastward very clearly, very continuously. And then over Eastern Pacific, well, not so clear, over the cold waters of Eastern Pacific. And it reappears here over South America. And you can see here that standing oscillation I showed you before in this time scale. Here, over Central East South America. And then it propagates into Africa, over the Atlantic into Africa. This propagation is very clear, is clearest when we look at the upper level zonal winds. Then it appears very clearly, even when you don't have convectively coupled propagation here. So it's very clear. But even here, at lower level, it is significant in the zonal wind. And here you have finally the impacts over South America. And I just want to call your attention here. Phases 8 and 1, you have highest positive precipitation anomalies here over Central East, South America. And these can reach, here you can see here, 4 millimeters per day in this region, which amounts to more than 10%, I would say around 12% of the climatological rainfall. Do you remember the first or second slide I showed? The average daily precipitation that was around 10. So, and these anomalies here are filtered anomalies. They are calculated and then filtered in the 20 to 90 band. So these are anomalies just in intra-seasonal time scale. Nothing of El Nino or interdecadal is included there. So just due to MGO or some other intra-seasonal contributes to 40% anomalies relative to the climatology, which is already a high value, the climatology in this region in summer. And yes, here it's an interesting question. The interaction between these mountains here and these rain bands here, when we have this zonal wind entering here, it seems that there is an interaction influencing the low-level convergence and shaping the distribution of the rain in phase 8. Now, let's see what happens in phase 1. So in phase 8, actually, what is responsible for these rainfall anomalies more here to the north is the equatorial teleconnection via Kelvin or eastward propagating Rossby waves. They actually, it's not a well-known issue, but this eastward propagating Rossby wave, they have a significant contribution. It's not just Kelvin. Okay, here we have the contribution of MGO, related anomaly, to the frequency of extreme events. I just want to emphasize that here in phase 1, do you see this isoline 2, isoline 1.6? This is the factor by which the normal, the climatological frequency of extreme events is multiplied. So it means that just due to MGO phase 1, extreme events in this very populated region is doubled. So you have double the frequency, climatological frequency of extreme events in this region. And of course, in phase 3, we have also an enhancement here by a factor of 1.6 here in southern Brazil. But the highest impact is here in the South Atlantic convergence zone. Okay, here I just wanted to emphasize how the vertical velocity anomalies move eastward, how they are enhanced over South America in phases 8 and 1. And here we have strong subsidence at the same time over the maritime continent. In phase 8 and 7, this southeastward shift here of the upper level divergence into this region. And okay. And just to show you how these anomalies here are caused during phase 8, mainly due to equatorial teleconnection. And you can see here in phase, these are the considered wet phases with regard to South America, although in phase 6 you don't have here these anomalies. In phase 7 also nothing very strong. It starts really in phase 8 and 1. And you can see that you don't have here extratropical wave trains between Pacific and South America. But in phase 7, something starts to happen here. In phase 8, you have already something formed. And in phase 1, you have this important cyclonic anomaly which enhances the SACs. So the question is, where from comes this forcing of this extratropical teleconnection, which is so important for these convection anomalies over the SACs? When you look here, it seems that it comes there from Australia, all the way here. There is a very clear wave train here. But actually, that's not the mechanism. So let's show very quickly here. If you take in phase 8 the divergence anomalies, those that seem more important, well, I don't have time now to show you how these influence functions work, but they show you the regions in which the anomalous convection, and which produce anomalous upper level divergence, are most efficient in producing rotational anomalies around certain target points. So which target points am I interested? In this circulation over South America associated with the enhancement of the South Atlantic convergence zone. So these 2 points here, the target points, so are this one and this one. And you can see that here in central subtropical Pacific, you have for one target point and the other, very strong influence function of opposite signs, showing that divergence, anomalous divergence here, will produce anticyclonic circulation here and cyclonic circulation here. So let's test it. And you don't see much influence from here, from Australia, from Indian Ocean, even not from Northern Hemisphere, but here. So this here is a very important feature of the anomalous convection for producing impact over South America. So when we take all these here, the most important in the equatorial region and here in the subtropics, so this is the idealized divergence anomaly I prescribe it for the model, I am able to reproduce very well what happens here in the southern hemisphere. Okay? Not here, of course, because I am not taking into account the other divergence anomaly, even not the divergence anomaly due to the convection over South America itself. Okay? Just what causes this connection here, which is responsible for these cyclonic anomalies. Well, okay, so I used all of these and got the right answer. But then let's see which part here is responsible for the connection with South America. When you take just these strong upper level conversions over the maritime continent, here, you get this part of the wave train, which is this here. Here, this part. Nothing going into South America. When you take this part here, you also don't get the right answer here. On the contrary, it's the opposite answer. But then you prescribe, and when you put both of them, the two most important, you get this part here just, here, but not over South America. But then you prescribe this here, which is this, and you get the connection with South America. So that this is a place to monitor, to see if you will get this influence over South America. Huh? And well, here just to let you know what Rongfu talked today in the morning. Yeah, what happens over South America is very important in shaping the anomalous circulation in the northern hemisphere. So if I prescribe here the anomalous divergence associated with phase 1 over South America, you get this strong wave train here, and a wave train here over South Atlantic and Indian Ocean, which produce here the right anomalies to favor the initiation of a new MGO cycle. So we are now looking into this, the occurrence of primary and successive MGO events, and what's the role of South America convection in this continuation of the MGO cycle. So a student of mine, Luana, is working on this, and the results are very interesting, but I'm not going into this now. Okay, so now just to finish here, you can see that in phase 8, you have these anomalies. This is frequency of extremes, more to the north. In phase 1, you have them spread all over this region here, okay? Phase 2, only here in northeast Brazil. So you can see that what we see here in phase 1 is actually the result of different mechanisms. The equatorial propagation, teleconnection, and the extratropical, which produces this anomalous convection over South Atlantic convergence zone. So here we divided phase 1 and phase 2 in subphases. Instead of on average 6 days, on average you will have 2 days here. So it starts here in the northern part. And then the extratropic teleconnection produces these anomalies here over SACs. And then this propagates here, and then fades away here, but remains here over northeast Brazil. That's why northeast Brazil is a region of very strong contribution to intra-seasonal variability. So I wanted just to show you but I don't have time. Iracema, where are you? Okay, so how are we with the, we started late, but I don't remember exactly when I started.
12:20 now.
12:20, okay. So we started.
Another talk.
Yes, there is still another talk. So let me see, 12:20. Okay, so yes, I will finish here. This is just to show you that here we have separated the synoptic variability and the intra-seasonal variability in the 30 to 70 days for an event, for a composite of very extreme events in the South Atlantic convergence zone. What's shown here is that, well, I will not read all of this. You can look, it's published in Climate Dynamics 2015. What is shown here is that we have here over the SACs a negative zonal stratic deformation. Well, this region with negative zonal stratic deformation increases the longitudinal wave number of the synoptic circulation anomalies that get here to this region, leading to a reduction of the longitudinal wave speed and increasing wave energy density or wave accumulation in this region. And this results in intense convective activity. In other words, these synoptic anomalies that get here, get into a region of where this happens, negative zonal stretching, but this negative zonal stretching is enhanced by the 30 to 70 day anomaly. And so, well, I don't have time. These synoptic anomalies, they are elongated and are trapped here and are superimposed on the intraseasonal anomalies. And this leads to very extreme events. This is a composite of extreme events in summer and SACS. So it shows the interaction between influence of Madden-Julian band and synoptic bands. It's very interesting, but I don't have time to get into it. This also. And this here, I will show tomorrow a little bit about this. Okay? Okay, then. Any questions? No? Okay, then Marcelo. So now we'll have a talk from another member of the working group on American monsoon, Marcelo Barreiro, from the Universidad de la República Montevideo, Uruguay. So this here.
This here. Oh, okay. Perfect.
Did you download? Yeah?
I have it here.
Let me just get out of here. I am not good. I'm not very good. Oh, no. Where should we go here? Oh.
That's mine.
This is
mine.
I wanted to take mine out. But
let's do this. You can take out.
Okay. Well,
yeah.
I guess I can do it. If you want to put it down.
Okay. The other way around. No. Okay. Okay. And this should be the pointer. Okay. Okay. Sorry for that. Well, good morning, everyone. Thank you, Alice, for the invitation. Do you hear me, or do you need this? For what is this for?
This is that the camera can track you.
Oh, I'm being followed. Okay. Oh, look, that's interesting. Okay. Well, let's start again. Hello, everyone. I'm going to talk about today, well, this is really about the remote and regional controls of the South Atlantic Convergence Zone. And as you know, the South Atlantic Convergence Zone, everybody knows what it is now, so I don't have to go into details about this. Alice has done a great job telling you how complicated the South Atlantic Convergence Zone is, right? It has many timescales of variability. And I guess I wanted to show you this picture just to summarize many of the different processes and climate modes that influence the SACC. For example, we know El Nino, the MJO, tropical Atlantic variability, the southern annular mode. All these climate modes can influence the SACC. And then once the signal comes into play, comes into the region, it is modulated by land-atmosphere interactions and ocean-atmosphere interactions. So one of the main ways the remote signal comes into the SACC is through the transients and on different timescales, and Alice has shown you several examples of that. So one of the main problems in simulating the SACC is that you really have to capture the relative importance of all the different processes. So if you go to a model, probably it's going to capture better one of these processes, for example, land-atmosphere interaction, or might capture better the path of the transients that leads to different SACC configurations. But I'm sure there's no model that can do everything right. And I think everyone will agree with that. Nonetheless, we can learn a lot about the SACC dynamics using models. And that's what I'm going to do today. And before going to short timescales, I want to first go into long timescales, and particularly about trends in the SACC. And let me show you this picture. This picture is the trends in rainfall during summer, 2010, 2060. It's only one model, okay? One model initialized with different atmospheric conditions. This is just one IPCC model initialized with different atmospheric conditions. So as you can see, you have regions that have a very consistent signal, I would say here. But then if you look at the SACC region, you can get anywhere you want, just depending on the initial atmospheric conditions. So the trend in this model, what we would like to call climate change signal, is very hard to get in the SACC. So if you take two of these runs, you have 40, you can take the 4th and the 9th run. You can see that in the SACC region, the signal is quite different, which is different from here in the ITCC, more to the north. Both runs tend to show an increase in rainfall. So trying to understand what the SACC should be doing in the near future is actually one interesting question that we should try to address. I'm going to try to go into some of this what we have been doing, particularly because recently has been published a paper, I think by Seeley et al., saying that the SACC should be shifting south of its climatological position. So is that what we should be expecting? Because if we follow this model, I mean, which one do we choose? This one or this one? It's exactly the same model, same forcing, different initial conditions. So if you go to climate change problem, and if you're worried about how much the temperature will increase, what you care is about getting the relative forcing right, which nowadays the main uncertainty comes from aerosol forcing. And among all the different feedbacks that you have, the cloud feedback is really the most uncertain today too. But that if you worry about how much the world will warm. But supposedly I want to know the changes in the regional precipitation. What does matter? And if you go into this question, it's a completely different story. What does matter is not this really relative forcing or climate feedback. It's really the patterns of sea surface temperature globally, and particularly in the tropics, and the internal variability in mid-latitudes. And once you get the signal, the regional land-ocean process will modulate what you get. So if we want to know what the SACC is going to do here, we really need, it's going to depend really on these issues and not on the relative forcings or the climate feedbacks that you want. So what does the global mean warming look like today? This is the zonal mean global temperature anomaly. And as you can see, there is well, this is 1890 and to 2010. And as you see, well, it was cool, cold to some particular reference period, and then started to warm, and the northern hemisphere warmed up than the southern hemisphere. Okay? And this gradient, this interhemispheric gradient of temperature, it has been increasing and is, projected to increase even further. So the question is, one question I can ask is, how should the SACC respond under this interhemispheric temperature gradient? We can also look into interdecadal oscillations. And if you look at the pattern of the Atlantic multidecadal oscillation, there tends to be warming in the northern hemisphere and cooling in the southern hemisphere. Again, it's an interhemispheric SST gradient. So the question is, how is the rain bands in the tropics, and particularly in the SACC region, will change to an interhemispheric gradient of temperature? We know that if we put a gradient of temperature between the two hemispheres, in particular here, the northern hemisphere cools because you have more ice in the northern hemisphere high latitudes, and the southern hemisphere warms, you get a shift of the ITCC toward the south. And if you, for example, take an AGCM and couple to an ocean slab model, and you put an interhemispheric gradient of SST, the ITCC will shift always towards the warmer hemisphere. So the question is the SACC going to do the same? Okay. So this is what I would call, I'm going to talk today about the remote response. How does the SACC respond to an interhemispheric gradient of SST anomalies? And then something that Alice didn't touch upon is that, is there any role for the regional ocean-atmosphere interaction in SACC variability? So essentially, I'm complimenting Alice's talks very well because she talked about shorter timescales and also on a different aspect of the coupling. So let's look into the first question. So it's the response of the SACC to an interhemispheric temperature gradient. And I'm going to use a simple atmospheric model, which is the ICTP AGCM, which is called SPEEDY sometimes. And the ocean is a slab ocean. This doesn't work. Okay. The ocean is a slab, so essentially it can interact with the atmosphere only through thermodynamic coupling. And I have to include a Q flux in order to simulate correctly the seasonal SST cycle. So I'm going to perform essentially 3 experiments, or 4 experiments, all 40 years long. And there is one control configuration. We have just a SST, the climatology. And then I'm going to put some extratropical forcing. One is going to be for the northern hemisphere plus southern hemisphere, one for only put the forcing in the northern hemisphere, and one only on the southern hemisphere. And we focus on DJF, which is the peak of the SACC. So this is the forcing I'm going to include. So I'm going to include a heat flux in the ocean that's going to warm the atmosphere above, and a cooling in the southern ocean that's going to cool this region. The idea is to get a pattern similar to the Atlantic multidecadal oscillation, or something similar to the trend we have today. You can note that the forcing is always poleward of 40 degrees north or south. There is nothing in the tropics here. And it has 0 global mean, so I'm not really increasing the heating. So what do we get? Well, essentially, what do we expect? You get a overall warming in the northern hemisphere, overall cooling in the northern hemisphere that extends toward the tropics. You can see that I did not include any signal, any forcing in the tropical region, but the atmosphere translates this signal toward the tropical region. And if you force, this was the forcing in the northern hemisphere and southern hemisphere. If you force with the northern side of the forcing only, essentially you get the northern part. And if you force only with the southern cooling portion, you get the southern part. So essentially, there's a quasi-linear response of the model to the northern and southern components of the forcing. So this is the temperature, the surface air temperature. So what does the model do regarding precipitation? So this is what it does. So if you see the lines, this is the climatology of the rainfall in the model. And where it's blue, it decreases the rainfall. Where it's yellow, red, it increases the rainfall. So with this forcing, what you expect is a weakening of the South Atlantic convergence zone in the northern side and a shifting toward the south. Okay, which is not what if you would have said, okay, the SACC should behave like the ITCC, so it should shift toward the northern hemisphere. So that's not happening. So actually, what the SACC is doing is actually shifting the other way around. Okay, and if you look here, there's another rain band of strong convergence that we call North Atlantic Convergence Zone. I will come back to that in a few minutes. But before going into this, what happens if this is the same plot I showed you before, and this is what you get if you force only with the northern side of the forcing. So you warm the northern hemisphere. You don't touch the southern hemisphere. And this is what happens if you you put the forcing only in the southern hemisphere. So the total response to both components of the forcing is really very similar to the model results when you only force with the northern hemisphere forcing. So the northern hemisphere warming is controlling the southward shift of the ITCC. It's not the southern part of the forcing that is controlling the SACC, even though the SACC is in the southern hemisphere. Okay? On the other hand, the ITCC is controlled by both the northern hemisphere forcing and also the southern hemisphere forcing. So one thing that we have to keep in mind is that when you force with the northern hemisphere forcing, the tropical North Atlantic here warms up significantly. And that is an important part of the signal. So what happens if you look at the circulation, you look at the divergent circulation. So you look at the velocity potential and the divergent winds at upper levels in 200 hectopascals. This is the total forcing. This is the northern hemisphere forcing. This is southern forcing. And as you can see, you get a modification in the local Hadley circulation. So you have this is negative velocity potential. So the winds go this way. You don't see the arrows are very small. So they diverge from here and converge here. And if you only force with the northern hemisphere forcing, you get the same response in the SACC region, even stronger. Okay, so the southern hemisphere forcing actually is trying to go against this weakening in the South Atlantic convergence zone. So you have the wind divergence here and convergence in the upper level, so you decrease the rainfall in the northern part of the SACC. So why is that? So let's back up a little bit and try to understand why this is happening. And if you look at the control case, so we know that in reality, the SACC is located between the Bolivian high and the low in the northeastern region. So the SACC is essentially in the middle. Okay? And the same is happening in the model. So you have the Bolivian high and you have the low to the east. So here is the SACC. This is the rainfall. Okay? So, and we know that several people have been looking into this problem, and it's essentially saying that the position of the SACC depends on the response to the Amazon convection. Okay? So now, if you change the ITCC, you're probably going to change the Amazon convection. That's going to change the SACC. So what happens when you put the forcing is that you modify this structure, essentially. So now, what you get is you actually have a more symmetric heating in the equatorial region. So before, the heating was more displaced in the Amazon region, which is essentially to the south of the equator. And then we know by Gill's response to an atmospheric heating, you're going to have an asymmetric response in both hemispheres. But once you shift the ITCC northward, essentially what you're doing is putting the heating in a more equatorially symmetric place. And when you have a heating in the equator, you expect two hikes to the northwest and southwest of the heating. And this is what we get. You have a high here, and you have the Bolivian high displayed here. So that essentially weakens the SACC and creates these North Atlantic convergence zones to the northeast of the North Atlantic. So the idea is that when you have a warmer northern hemisphere due to the forcing, you warm up the tropical North Atlantic. That shifts the ITCC to the north. That now you have the heating released by precipitation is more located in the equatorial region, and that, according to a Gill response, you're going to have two anticyclonic circulations at both sides of the equator that weakens the SACC and strengthens the North Atlantic convective zone that we created here. And then once you have the North Atlantic convergence zone, that generates divergence in upper levels and convergence in over the SACC, weakening the SACC. So instrumental to all this mechanism is the fact that you have to warm the tropical North Atlantic, because that's what shifts the ICCC to the north. And so what we can do is repeat the experiment, but now fix the tropical SST. So you don't allow the tropical SST to change, and see what happens if to the SACC. Does it change or not? And this is what you get before, and this is what you get when you fix the tropical SST. Essentially, you reduce the SACC response by 75%. So the main issue here is that the warming in the North Atlantic that shifts the ITCC to the north, when it doesn't happen, you essentially do not have a response in the SACC region. Okay, so to summarize this first part of the talk, the idea is that in December, January, February, if you have an interhemispheric gradient of temperature, the SACC will respond to that. Okay, and in a way that is not the same as the ITCC would do. The ITCC will shift north, the SACC will shift south. Okay, so let's move to the other question I had in mind. And now let's go to shorter timescales. So once you get the signal into the SACC region, okay, it can be on any timescale you want. Okay, let's focus here particularly on synoptic and subseasonal timescales. Once you get the signal, does the Earth-sea interaction in the South Atlantic do something to the SACC? So the approach I'm going to talk about today is actually a combination of complex networks plus using a regional couple model. So I'm not sure if you're familiar with the idea of complex networks, but complex network essentially is a methodology that allows you to study any particular problem you have. Essentially, a complex network is a system of interacting agents. And in climate, these agents are essentially the grid points in a grid. So each grid point is a node. And different nodes, so that means each grid point is going to be connected in some way to another. Okay? So people have been using these complex networks for studying, for example, the continental routes of the plains, or looking at the internet. Places where they have a lot of connections to many other places are called hubs. So this would be here, that would be Houston, and New York City, and so you can choose. And then there are hubs also in the web. So places where people like to connect. Okay? Now we can do the same, but now we call this climate complex networks. And as I was telling you, now the nodes are the grid points in the field. So you have a reanalysis. Any variable in a grid, you have points that are connected among each other. And this can be connected in any ways you want. You can be just by correlation. It's the simplest way to connect to grid points. It can, which has no directionality, but has, these two are correlated, doesn't tell you which direction it is. But you can use other measures that allows you to measure directionality. So that means this point is connected to this point in this way, not the other way around. Okay? And for example, one technique that is very common to use is the mutual information that allows you to use that as a directionality measure. And the good thing is that whatever properties you have of the time series of this variable are going to be in the topology of the network you create. Okay? So today, what we are going to use is to define the link between different grid points using a directionality measure. Because what I want to do is to see if the ocean is doing something to the atmosphere in the SACC region, and how the atmosphere is doing something to the ocean in the SACC region. So you need a directionality that tells you which way is the interaction going. Okay? And the measure I'm going to use is the Granger causality measure. Okay? So I'm going to look at the daily timescales and in the SACC region using daily era interim reanalysis, focus in December to March. And I'm going to take one variable to represent the atmosphere, which is the vertical velocity 500 hectopascals. And the SST will characterize the ocean. Okay? So what we can do, how does this Granger causality measure work? Essentially what it does is, I have to assume that the evolution in time in a particular grid point in the atmosphere or in the ocean can be represented by an autoregressive model of order D. A D I have to find. Okay? So this is the autoregressive model of order D. So I have a variable y, which can be SST or omega. And what I say is that this variable can be written as a coefficient times the values of this variable in the previous times, plus the sum of coefficient times the other variable in previous times. So if this is SST, this would be SST previous time, and this would be omega at previous times. Okay? And what I do in this exercise is fit the model and look at the residuals. And fit the model fit the time series with the whole model. I get a residuals and a variance of residuals, which I call sigma square coupled. And then I remove the part that has to do with the other variable. I get rid of that. I say, okay, no, I don't. For example, the SST in my grid point depends only on the SST on the previous values of previous states of SST, but not on omega. Okay? So I set B sub k equal to 0. And again, fit the model, look at the variance of the residuals, and this is the Granger causality estimator. It's the variance of the uncoupled system minus the variance of the residuals of the coupled system divided by uncoupled system. So that means if the variance of the uncoupled system is larger than this one, what is called is that X is Granger causal of Y. So X is doing something, is giving some information on the evolution of Y. And this is what I get. So this, if I take one point in the ocean, and I look at the causality to the point in the atmosphere just above. Okay? Just above, and the same in both directions. Ocean to atmosphere, atmosphere to ocean. Okay? So if where is black, there is no causality. There is nothing. So if you look at the ocean to atmosphere, what you find is that there are essentially two regions where you have to find connection. Well, there's one region you have to find connection. We know that in the deep tropics, the ocean forces the atmosphere. You have to find it. If not, you're in trouble. So we find that region that in the ocean forces the atmosphere, but we also find a region here in the SACC region where the ocean is forcing the atmosphere. Nonetheless, if you look at the atmosphere forcing the ocean plot now it's the other way around, you see that in the SACC region, the main direction of interaction is the atmosphere forcing the ocean, which is what we expect also. Okay? But you don't see much in the deep tropics. So in the deep tropics, you see one-way essential interaction, so the ocean forces the atmosphere. In the SACC region, you have mainly an atmosphere forcing the ocean, but you also have an ocean forcing the atmosphere. So this point to point. One other way to that I can construct another statistics, which is called the area-weighted connectivity. And now I'm not looking just at one point above another. I'm just saying this point in the ocean, I want to see how it's connected to all the points in the atmospheric domain. And then take another point in the ocean. I want to know how it's connected to all the atmospheric domain. And then I do the other way around. One point in the atmosphere, I want to know how it's connected to the whole ocean domain. Okay? And this is what is called the area-weighted connectivity. Essentially, you create a matrix, A, which is called adjacency matrix, that you say to 1 if the causality is significant, and to 0 and if not. So this point with this one, with this one, with this one, with this one. Where the connection is statistically significant, I put 1. If this point with this point is not significant, the connection, I put 0. Then I sum up all the points, essentially, all the ones. The only thing I do is that I have to weight to a cosine because the areas are not the same, essentially. Okay? So this is the area-weighted connectivity. And this is what I get. So if I look at the ocean to the atmosphere, the area-weighted connectivity through the Granger causality, ocean to atmosphere, gives you this maximum in the SACC region. So there is a maximum in the deep tropics, which we expect, but the main maximum from the ocean through the atmosphere is in the SACC region. So the SACC region in the ocean is the region of the ocean in the tropical Atlantic that is most connected to the atmosphere, that is forcing the atmosphere in one way, in some way, somehow. Okay? Very good. So,
in which domain?
This domain.
This domain.
This domain.
Okay.
Yes. I could use it, the global theme, but I use this domain only. Yes. So we don't know the physics behind this. So I'll give you one example looking at the subseasonal or intraseasonal timescales. And I'm going to talk about the MJO that Alice introduced so nicely. And we know, Alice already talked about this, so we have a connection throughout the tropics, and we have an extratropical connection. So when the MJO moves, it connects, it influences the South American monsoon region, and also we have the extratropical connection path. So both are ways. in which the MJO can influence the South Atlantic convergence zone. So this is a paper of Alvarez et al. Where they study the teleconnections. Alice has similar plots, just to show you that that depending on the phase we are talking about, the teleconnections will be different. I'm not going to go too deep into this thing now. So I'm going to put together two phases, phases 2 and 3, 4 and 5, and 6 and 7. Okay? And this is the OLR, the anomalies of outgoing long-wave radiation in the SICC region. So you have this dipole that Alice mentioned before. It's not really the main weight is here. Here is weaker. So this is for phases 2 and 3, this is 4 and 5, and this is 6 and 7. Always in DJF. But together with these changes in the precipitation and OLR, so you have changes in the surface fluxes in the ocean. And these surface fluxes in the ocean, essentially you have an increase in the surface flux here because you have less rain here. Okay? And this increase in the heat fluxes in the ocean, essentially you go to the next phases and it warms up the ocean in phases 4 and 5. Yeah? So my question was, is there a role for these SST anomalies that the MJO creates in the cycle? So do these SST anomalies somehow modulate the signal of the SICC, particularly in the oceanic extension of the SICC? One thing I can tell you is that this kind of warming that generates the MJO in the South Atlantic is connected to the marine heat waves. The occurrence of marine heat waves in this region is strongly connected to the occurrence of the MJO. But marine heat waves are essentially the same as atmospheric heat waves, but in the ocean. Okay? So how are we going to look into this? Well, what we used is a couple model, which is a regional couple model, which is the RECCM 4.5 developed at the ICTP, together with the MIT OGCM at 1/8 degrees, 40 vertical levels. This couple model was developed at the ICTP also in Trieste. And we performed 2 experiments during 10 years. It has ERA interim in the atmospheric boundary conditions, and it has in the ocean has MOM 0.25 degrees as boundary conditions. And we essentially ran 2 experiments. One experiment with the standalone RECCM, so it's atmospheric model forced with SST, with observed SST. And the other one is the coupled ocean-atmosphere model itself. So the atmosphere and the ocean interact completely. And we run it. This model has been coupled for many different regions. We coupled it in this domain, in the South Atlantic, which is this blue box is the ocean model region, and this red box is the atmospheric model region. So we use this configuration of the coupled model. And this is what we get. So this is what I showed you before for the observations. And this precipitation, so the sign is changed here. So this is increased OLR is less precipitation. So it should go with negative precipitation here. So this is the coupled model for the same phases, same days. And this is for the AGCM standalone, same days as the observations. So first of all, what I want to point out is that the model alone, the atmospheric model alone, is doing a pretty good job in, capturing the dipole over the SICC region when it's forced with ERA interim boundary conditions. So I can do exactly the same composite because it has the information about the exact days. Okay? And this is what the coupled model does. So the coupled model has a much weaker signal, much weaker dipole than the standalone model. Actually, the standalone tends to do it too strongly compared to observations, and the couple model tends to do it, I would say, too weakly compared to the observations. So why is this difference? So essentially, what we find out is that Alice showed that when you have a decrease of rainfall here and increase here, you will have a cyclonic circulation here, which is shown here, the cyclonic circulation. This is the observations. This is the couple model, anticyclonic circulation, sorry, anticyclonic circulation. And this is the anticyclonic circulation when the REC-CM is forced with observed SSTs. As you can see, the anticyclonic circulation is much stronger in this case than in this case. It's actually much stronger than in the observations. And that is consistent with the fact that the rainfall anomalies are much stronger here than here and even here. So what would be the case? Well, what is happening, what we hypothesize, is that when you have a warming in the ocean, okay, we know that when the ocean warms, it can influence the atmosphere by changing the atmospheric boundary layer. So the surface winds, when you have a warming, tends to be stronger than when you have a cooling in the surface. Why is that? Because the atmospheric boundary layer destabilizes, and so there is more mixing in the atmospheric boundary layer. So it allows to bring more momentum from the upper atmosphere toward the surface. So if you look at the observations, so you have a warming here, and you have the maximum winds are essentially above the warming you have in the ocean. And when you force the atmospheric model with the observed SST, essentially the model tries to overdo it. It tries to respond too much to this bringing down momentum from the upper layers toward the surface. So it creates a very strong anticyclonic anomaly that is way too strong compared to observations. In the couple model, what happens is that you get the signal that comes from the extratropics, but you don't have a warming here. So essentially, the anticyclonic anomaly cannot strengthen, and you have a weaker signal compared to the standalone case. So the contour, just to be clear, are the wind speeds, and the colors are the SST. So here, the SST anomalies essentially don't change, and you have contours that essentially are very similar to observations. But these are much stronger. And this increase is due to the response of the atmosphere to the unstabilization of the boundary layer. So this is one way through which the ocean here, the SST here, can influence the atmosphere. And that's why the SST below the SSC region is one of the most connected regions in the atmosphere. So to summarize this part, we use a complex network approach to identify a two-way coupling in the SACC region. And as an example of this interaction, I show you that during the MJO, phases 4 and 5, an positive SST anomaly develops below the SACC that strengthens the surface anticyclonic circulation, leading to stronger precipitation response. Just to finish up a little bit of advertising, if any of you are interested in networks in climate, we published a book. It came out in April this year. So there are many different methodologies there that you can use to analyze the data. Thank you very much. Leila? Oh, sorry.
Leila or you?
Okay.
Have you done the experiment reversing the temperature gradient, warm and cold?
Did we? I don't remember, actually. I have to say, that was done by a PhD student of mine. I can't remember if he did that.
Because it's interesting that the southern hemisphere, the cooling in Antarctica did not have an influence, or possibly if you warm, something else would happen.
I think we did. I don't think we found any different results. Otherwise, we would have been published. But I have to be sure about that. Yes.
Very interesting explanations. Really find very interesting. But I have a question for you that I didn't understand very well in the last part of our talk. Because when we look at the SACZ and we try to look at sea surface temperatures observations, we see always related to cooling. Even when we filter, we look into relationships with the MJO, we always see the cooling, and interpretation has been radiation related.
Yeah, that's exactly here. That's exactly here, because maybe I wasn't clear enough. This is positive OLR, so that means it rains less. So you have stronger shortwave radiation coming into the surface. Let me show you here. The net heat flux increases particularly because you have less rainfall. So it's exactly what you're saying.
But when you have it organized, the opposite, right?
That would be in phases 1 and 8, I think, what Alice showed before.
Yeah.
When it rains, I didn't look at this into these phases, 8 and 1. As you see, it's 2, 3, 4, 5, and 6, 7.
Oh, I see. Okay, thanks.
Yeah, but that's exactly the mechanism we are talking about. Yes.
Yeah. Thank you so much. Very illuminating presentation. I have a question about the southern hemisphere heating. It looks pretty zonal symmetric, right? And did you consider the cooling due to ozone depletion? And if you include that, whether the southern hemispheric influence, the cooling would have a stronger influence.
So what were you suggesting? What kind of pattern are you thinking?
Well, I was thinking because the stratospheric cooling due to ozone depletion is actually so far it's far more dominant than the greenhouse-induced stratosphere cooling. So the cooling you prescribed there, is that mainly the greenhouse or?
No, well, but the thing in the cooling here, I'm putting the cooling in the ocean. Oh. Not in the upper levels.
Oh, because
not in the upper levels.
The upper level, you
no, that's a completely different story.
Result. Yeah,
no,
because then the jet will move forward, and that would have a quite strong influence on the SACZ. Yeah.
No, I wanted to reproduce actually this kind of pattern.
Okay, I see.
So warming in the northern hemisphere, cooling in the southern hemisphere.
I see.
So a slab ocean allows you to put an anomalous Q flux. Mm-hmm. So you don't change the SST directly. You essentially put an anomalous Q flux that translates into an anomalous ocean heat transport.
Yeah.
Okay.
That raises another question. The reason the southern hemispheric cooling seem to have a weaker influence is really you don't have as strong of ITCZ as the northern hemisphere, right?
Because it's located in the northern hemisphere, ITCZ. That's what you mean?
Yeah.
Well, but
ITCZ communicates the surface warming through the whole troposphere, and then you see ITCZ moving northward in responding to northern hemispheric warming, and that influences SACZ everything. But in the southern hemisphere, you don't have ITCZ pretty much in the Atlantic or East Pacific.
Well, but it's December, January, February. Well, it's the most southward you can get, essentially.
Yeah. Okay. But
yes.
ITCZ is still pretty much.
These are anomalies. These are anomalies. So the ITCZ really shifts toward the north. No, the ITCZ moves toward the north because of the warmer hemisphere.
I think my doubts are somewhat similar to those of Leila. Let me see if I got it. So,
yes.
When you have a dry phase there in Central East South American, phases 3, 4.
Oh, okay.
Okay.
Okay, let's go to the other one.
So you have positive SST anomalies because you don't have cloudiness. Okay, it's raining below normal. So what you concluded is that this SST anomaly produces an even stronger anticyclonic circulation which persists even longer the precipitation anomalies.
It will strengthen the dipole, if you want to call it, over the ocean, particularly. So if you look at the response here, so this is essentially the anticyclonic anomaly without no coupling with the ocean. And this is when you put the forcing, the local forcing. So if you look at the extratropical part, this part is essentially the same. But if you look in here, this anticyclonic signal is much stronger.
So then the precipitation anomaly would persist more because of these induced SST anomalies. So you are concluding that there is a positive feedback of the SST caused by the precipitation anomaly, cloudiness anomaly.
Well, the thing is, I'm not sure if I would call it a positive feedback, because once the MJO starts to changing all the circulation patterns, it will kill it. But it will be able to strengthen it during a week or so.
I am a little bit in doubt about this because I have seen a tendency to reversal when you have these negative rainfall, not very soon, let's say, but you have negative rainfall anomalies in this region of the Sahara. Then you have increased SST anomalies, okay? And over the land you have less soil moisture, higher temperature, pressure, surface pressure is lower. So you get a cyclonic anomaly there, and which redirects the moisture flux, and then it gets wetter than normal.
That's
it's not in the time scale of MJO.
Yes, exactly.
But the chain of the events is in this direction, not in terms of persisting.
But this is mainly over land, right? What you're talking about?
No, it involves also the SST. Yeah. So the SST being above normal would be a factor of helping to reverse the precipitation anomalies, because when you prescribe in this region warmer SST, usually the atmosphere responds with more rainfall. It's not as observed when you don't have coupled mode, okay?
Yeah.
When you prescribe it.
Yeah.
But, there is some kind of feedback, because this region of higher SST, lower SST, it also moves according to the band of cloudiness, and it can feed back into the atmosphere.
Yeah, I guess the main difference there, I think, in the mechanism you're talking about is mainly about moisture fluxes, right? And here it's about destabilizing the atmospheric boundary layer and bringing momentum downwards. I think there are two possibilities. Maybe there is a combination of the two.
Mm-hmm. Okay.
Hi.
Hello.
This band that you called North Atlantic Convergence Zone is a real convergence zone, or is just a band of cloudiness?
It is located similarly as the South Atlantic Convergence Zone. When you do let's go that one. If you look at the upper level flow, Where is it? Here. See, you have the high, you have a trough here, and you have the trough here. So essentially, it's symmetric. It's symmetric because essentially it's similar to the Gill response when you put the heating on the equator.
But this is result of your model.
Yes, that's when you force the model with the interference gradient.
Have you seen this in the observed?
Actually, I haven't looked at that because this is a sensitivity run to see what will happen when you have a strong interference gradient. Maybe we will start seeing it.
Just another question.
Yes.
Quickly, do you think this over-intensification of this circulation could be given from the parameterization of the boundary layer in the model?
Not really. If you look at the main response of the atmosphere to an oceanic warming or cooling for spatial scales in the ocean close to mesoscale is actually an intensification of the surface winds when you have warming. That's the main response. That has been shown in many different observational data sets and models. So it's actually something that, that has been observed. No, I don't think it has to do with that.
Okay, thank you very much.
Sure.
So now, finally, lunchtime. And so please be back till, let's say, 2:30. It's okay? 2:30. Okay.
Is there a place to eat here? Is there a close place to eat?
Ah, yes,
Close
there
by.
are many places here around to eat.
We go outside or?
Yes, we are going outside.
Ah, okay, good. Hello. Yes. Well, none of the models show. I mean, supposedly you would say you expect a slowdown of them. We agree with that. But the thing is that the warming is going to be still larger in the northern hemisphere because of changes in the surface. So the ocean will not dominate.
Actually, the ocean will be one.
In the northern hemisphere and the southern hemisphere.
Because I would think that
Definitely. No, as long as I've seen for projections,